In the final piece of our power puzzle, let's look at something called apparent power. And so we know that our complex power has a average or real component and has a reactive component. But the length of this vector here, so the length of this line here is called S. And it's not S with a hat. It didn't come to the party with a hat. It's just S as a scalar. And S is called apparent power. And so what S is going to be the magnitude of the complex power variable. And so because this is a triangle right here, we can say that our apparent power is equal to the average power squared plus the reactive power squared and the square root of that due to the Pythagorean theorem. And so when we punch in our different formulations for real and reactive power, so that'd be V RMS squared, or V squared, and then this would be our cosine of the angles squared plus V RMS squared I RMS squared sine of our phase squared, and then all of this square root. When we can start to sort of bundle things together, then we will have inside of our big square root V RMS squared I RMS squared, and then the cosine of this angle plus the sine of this angle, so our phi z angle here. And cosine squared plus sine squared, when you group them all together, ends up being 1. So our reactive power is simply VRMS times IRMS. Sorry, our apparent power. So our apparent power S is this value here, and the important thing to remember is that S is not equal to S hat. This is the complex power, and this right here is what we're going to call the apparent power. And the apparent power is just sort of the total magnitude of everything going on. That's the totality of all the power sent in, and the complex power breaks it up into its individual components. The units for our apparent power are going to be in volt amps. So not watts, but volt amps.